Dear students, today we'll discuss on motoring and electric braking operations of DC shunt, separately excited and series motors, and numerical problems related to this topic. Yeah, in the previous class we have discussed the torque speed characteristics of DC motors, and we were able to determine the speed and armature current. One second. The speed and armature current of the DC motor for new values of voltage and field current. We should extend that idea for motoring, dynamic braking, and regenerative braking operation. Yeah. So the discussion today will be on motoring and electric braking of a shunt, separately excited, and DC series motor. And by the end of the class, you should be able to determine the motor speed and braking resistance. That means external resistance that is to be included in the motor circuit to get required current or torque or braking operation. So what is braking of DC motors? The braking of DC motors is the method in which the DC motor which is running is to be slowed down or stopped. So controlled slowing or stopping of a motor and its driven load is as important of starting in many applications. When you are starting the DC motor speed starts from zero and reaches the rated speed. We know different starting methods. uh, Similarly, when you want to stop the motor, the braking, for example, in cases where heavy loads are picked up by the cranes and traction on a slope, let us say the train is moving down the hill, we shall consider an example for a discussion. In that case, the speed tries to increase. So, what should be the braking method that is to be applied that is to be employed in these cases? So, braking of DC motor methods are based on friction, electromechanical action, eddy currents, etc., are independent of the motor, but sometimes electric braking is better justified owing to its greater economy and absence of brake wear. So this important point here. There are different types of braking that can be done. For example, in vehicle, when we want to stop, we are applying a mechanical brake on this one. So because of the friction, it stops. So I can go with mechanical braking or electromechanical action or eddy current action, but electrical braking method is best suitable, which has more advantages than the other. The DC motor is still being widely. Is the DC motor used in applications? Yes, we discussed in the previous classes also. Even though the AC motors have gained their application in industry, but there are some critical loads such as cranes, hoists, and the rolling mills, where heavy load and heavy transient operations are there. Fine speed control is required. Regenerative operation is required. DC motors are best suitable. So one of the main reason for using a DC motor is the excellent braking characteristics and the ability of smooth transition from the motor to generator operation or mode. During braking period, the motor is operated as generator and the kinetic or gravitational potential energy. It may be rotational load or it may be linear load like cranes and hoists. The heat or the energy is dissipated in the resistors by the method called as plugging, or the excess energy can be returned back to the supply in case of regenerative braking. So there are different possibilities of braking techniques possible in case of DC motors. Let us see next. So there are three main types of DC braking of motors, that is DC motor braking methods. One is regenerative braking, second one is dynamic braking, and third one is plugging. In regenerative braking, what we do, in dynamic braking, what we do, in plugging braking, what we do, and how the braking operation is achieved, we shall discuss in detail one by one. Yeah. So coming to the first one, regenerative braking. What is done? In regenerative braking, generated energy is supplied to the source. We are now actually discussing the motor. Motor does what? It takes electrical energy and gives mechanical energy. Now, if this mechanical energy becomes more than the electrical energy, the motor turns into a generator, and this excess energy, whatever that is available, can be supplied back. So, what is that is to be done in case of regenerative braking? The generated energy is supplied back to the source. So if we have a system where the source is capable of absorbing power, then we can implement the regenerative braking. When is this possible? We have equation for any motor in general. V is equal to what? EB plus IA into RA. Now the applied voltage is used to meet the armature losses and generation of back EMF. This back EMF is converted into mechanical energy, and its electrical equivalent power is EB into IA. If by chance EB becomes greater than the voltage, this is what, when EB becomes greater than the voltage, then current becomes negative. So here see IA is equal to what? V minus EB divided by RA. So then what if, for example, EB is greater than V, then current becomes negative. When does EB becomes greater than V? There are many possibilities. We have EB is equal to what? KE phi into omega m. If let us say this speed increases beyond the rated speed, then EB will become greater than V. And another one, if by chance I decrease the voltage intentionally, then V becomes less than EB, and then also current becomes negative. Regenerative operation takes place. So let us analyze this thing, what happens in terms of the characteristics. Under normal operating condition, the motor characteristics, torque speed characteristics of the motor for the separately or shunt motors will be in the first quadrant. So if, for example, I decrease the voltage, then the motor characteristics comes down. If by chance the speed becomes, if by chance I decrease the voltage and I want to go with braking operation, then what happens? If I decrease the voltage for some time, V will become less than EB, and the characteristics moves like this because the current becomes negative and the torque becomes negative. Motor torque becomes negative. You will now enter into braking mode of operation. So by decreasing voltage, maintaining the flux constant, by decreasing the voltage, EB becomes greater than the supply voltage for some time, and hence the motor speed tries to decrease. If we decrease the voltage, then the speed comes down to zero fast. Okay, that is what will happen. Okay, the other way what we can do in the braking operation is that let us say we are applying the decreasing the flux at constant voltage, then what happens? The speed will be greater than the rated voltage. We know that speed and flux are inversely proportional. This we'll also discuss in detail in the next topic of speed control methods. And now with that case, the characteristics will be upwards. Okay. Yeah, let us take an example. What happens when let us say a truck or a train is moving up the hill? So as it moves up the hill, what happens? Once it reaches to the place here, the load torque becomes zero, and then here coming down, then what happens? The speed increases to a large value. So here the regenerative braking operation is possible during the downhill. That we'll discuss. So for motoring operation, when the vehicle is moving upwards, for the motoring operation, the characteristics is like this. So that is a T uphill, the torque speed characteristics. Let us say the torque that is required by this is T uphill or TU, and corresponding speed will be, let us say, here. Okay, corresponding speed will be here. Now, this portion 1, 2 will be the characteristics that will be guiding during the vehicle moving upwards. Now, when the vehicle has reached to this point, the torque is zero because there is no torque, and hence let us say the speed becomes zero. Then we have the operating point 2 here. Next, T downhill, when the torque is moving downwards, then what happens? The speed becomes greater than the rated speed, and hence EB becomes greater than V. Current becomes negative, torque becomes negative. So therefore, torque speed characteristics will be in the third quadrant now. And what are the equations that will guide for all these three regions? We will see. For that, first we will consider the basic equations. Let us consider a shunt motor with EA, RA, RF, IF, IA, I and VT, and speed is omega. So now what is the terminal voltage VT? VT will be equal to what? EA plus IA into RA, and this EA is given by the back EMF EA is what? KE phi into omega m plus RA into IA is nothing but what? T divided by K into phi. We have already discussed these equations. And speed omega m will now become Vt by Ke phi minus Ra by Ke square phi square into T. So therefore Ia will be equal to what? Vt minus Ia by Ra, Vt minus Ea by Ra. This we get from the circuit. And from the torque equation, Ia is T divided by Ke into phi. So these are the equations. Now let us come back to a vehicle moving uphill and downhill. So this is the range of, so at the operating point 1, that is during uphill, let speed be omega 1. So omega 1 will be equal to what? Vt by k phi minus Ra by k phi square into T uphill. Okay. And Ia1 is Vt minus Ea1 by Ra, and that is T uphill by k phi. This is positive current, and Vt is greater than E1, and hence it is motoring operation. And hence it is motoring operation. Now at 2, what is happening? The speed omega 2 is Vt by k phi, because at that case the torque is 0, Ia is 0, and hence there are no Ia into Ra drop. So this point will go, and hence Eb will be equal to voltage by this one. So therefore, our EB is equal to VT. Okay, let me tell here. VT is EB plus IA into RE. So at this point to 2, torque is 0 and hence current is 0. So this term is 0, and hence EB will be equal to VT. So omega 2 is EB by K phi, which is nothing but VT by K phi. So Ia2 will become 0. Ia2 is 0 because torque is 0, TL by K phi, and Vt minus Ea2 by Ra. So at this point, Vt is equal to Ea2. At point 3, during downhill, what are the equations? Omega 3 is Vt minus Vt by K phi minus Ra by K square phi square into T downhill. So what is the observation is here? This omega 3 is greater than this speed. See here, greater than the speed and greater than the no load speed. Speed has increased. So omega 3 is greater than omega 2 and greater than omega 1. So what will happen now? Your EA will become greater than the terminal voltage. In this case, we will call it as EA3. So IA3 is VT minus EA3 by RA or T downhill by K phi. As EA3 is greater than this one, current is negative and then torque is negative. So VT is less than EA3 or EA3 is greater than VT. Okay, these are the things. So now we shall, here we have considered what? Speed versus torque. Okay, if I take speed versus back EMF, speed versus back EMF, okay, EB or EA, whatever it is, then what happens during the starting? At starting, speed is 0. So therefore, back EMF formula is what? EB is equal to Ke phi into omega m. At starting, omega m is 0. So therefore, back EMF is 0. And let us say it is a shunt motor. So flux is constant. So it is a linear variation. So as the speed increases, back EMF also increase. At one stage, is, let us say omega 1 is the T uphill point. At that condition, this is the back EMF that is developed, and this is the terminal voltage V point. EB is equal to V point. So under no load condition, EB will become equal to V, and under downhill portion, then the speed will become greater than these two, and hence you have negative current and negative torque. But back EMF is positive. Okay. So these points once again pictured in this table, you can please go through this. So let us take a problem on this one. A 440 volts DC motor has a rated armature current of 76 amperes at a speed of 1000 revolutions per minute. So motor voltage is given, armature current is given, speed 1000 RPM is given. The armature resistance of the motor is 0.377 ohms and the rotational losses is 1 kilowatts. The load of the motor is bidirectional. The load of the motor is bidirectional. This is important. So calculate the no load speed of the motor. Okay, we have discussed these things in the following slides. One second. Yeah. So we shall take one by one. Calculate the no load speed of the motor. To calculate the no load speed, you need the back EMF relation. So therefore, first you are finding the back EMF. Yeah. So back EMF EA is VT minus RA into IA, and hence you can find the back EMF is 411.35 volts, and KE into phi is nothing but EB by omega, and that is 3.93. So once you know this, we can use this value, constant value, for the next conditions. So under no load condition, omega naught, what is the no load speed? It is nothing but VT by KE into phi, and that becomes 111.96 radians per second. Next, what is asked? If armature current is 60 amperes during regenerative braking, calculate the motor speed. So what will be the motor speed during regenerative operation? During regenerative braking, IA is 60 amperes given, then omega 3 will be equal to what? VT divided by K5 minus RA divided by K5 whole square into TL3. So substitute and you will get the speed as 117.72 radians per second. Next, what is asked? Calculate the load torque during regenerative braking. What is the torque that is offered by the load? So that is TL3 is nothing but KE5 into IA3, and you know all the values, and hence it becomes minus 235.8 Newton meter. You can see now the torque is negative, and EA3 back EMF is 462.64 volts. So next we can find the power developed during motoring operation and during the regenerative braking. So P1 is IA1 into VT, and that is 33.4 kilowatts, and PG is EA3 into IA3, that is 27.76 kilowatts. So we can find out power, new torque, new speed under different conditions. Yeah. So now let us consider the case where regenerative braking is happening. That is regenerative braking during speed reduction by reducing the supply voltage. In the previous case, speed has increased and EB has become greater than V. Now, if supply voltage is decreased, what happens? So, if for example the motor is operating and its speed torque characteristics is like this. So it is operating at, let us say, full voltage V1. Okay, and the load torque is T1, therefore the operating point is 1. If, for example, we decrease the voltage, then what happens? When we decrease the voltage, there is a possibility that this V becomes less than the back EMF. What is the back EMF at this instant? Let us say EB1. So if V2 is less than EB1, then there is a chance of regenerative braking operation. So your new speed torque characteristics will be downwards, and the operating point for that for that speed, for that voltage, this will be the operating point now. So yeah, straightly taking this operating point to 2. So now For this, what is the no load speed? That no load speed is omega naught 3. Okay, so it has to, now what happens, the speed is here and then gradually decreases. So now if we allow like that only, then gradually the speed decreases and hence it enters into again the motoring operation. Okay, if not, if we go on further decrease the voltage, so it may be like it may come here and again you are decreasing, it goes like this, it goes like this, and then speed can be decreased. Okay. Yeah, so during dynamic braking, the second method is the dynamic braking. In this case, what you are doing in case of dynamic braking, the armature winding is connected to the external resistance. Let us see here. This is motoring operation. A separately excited DC motor, field winding is connected to the supply, and armature winding is connected to the DC voltage V. Now, if we remove this voltage and connect resistance here, then what happens? The back EMF in the motor will supply the current to the external resistance. So the current direction is also reversed. So let us see here. So braking with separate excitation. For separately excited motor, if I disconnect the armature winding from supply and connect an external resistance, now armature current direction is reversed. Okay. So with that, what happens? Now it is nothing but a battery connected to a resistor. So the characteristics will be linear. So the speed torque characteristics will be like this. Let us say the value of this braking resistance is RB1. So for this RB1, the speed torque characteristics will be like this. And if I vary the resistance, it will go like this. So the slope of this curve will change, and hence now what will happen? The motor which was operating with this, suddenly if I remove the supply and connect the external resistance, it will move on to this point and follow this one, and hence the speed becomes zero fast. So that is what is dynamic braking. But what is the disadvantage in this? As current is flowing through the external resistance, there will be I square or drop, and hence the losses exist in this system. Okay. In case of self-excitant for shunt motor, then what happens? You are connecting external resistance. The almost similar operation goes for separately and self-excitation motors. Yeah. So now what is that? External resistance is connected now. Now what will happen now? What will be the current IB, the armature current during braking operation, during dynamic braking operation? Let me call it as IB. Now this IB is reversed to the direction of IA, and hence IB will be equal to what? Minus EA divided by RA plus RB, or minus K phi omega by RA plus RB. So power developed is nothing but EA square divided by RA plus RB, and K phi omega whole square by RA plus RB. Yeah. So this is what I was explaining previously. During motoring operation, the speed torque characteristics is like this. So if I suddenly go with the dynamic braking, external resistance is included, and I can vary the resistance to any value and make the motor to come to to zero speed in required amount of time. So depending on the resistance, it takes some time. In between, I can also vary the resistors also. Okay. So you see here, IB is nothing but minus EB by RA plus RB. So this is the braking resistance included. If I increase the braking resistance, braking current will decrease. So this is less value of braking current. So for less value of braking current means more resistor. So it means what? RB1, RB2, and RB3 if we take. RB3 is greater than RB1, RB2 is greater than RB2. So this is one. See, another experience that you have to know is dynamic braking for unidirectional load. Load torque is not becoming negative. In that case, what happens? The point A, instead of going to point B, it's continuous line as we have seen previously, that it extends like this. Okay. Now it goes to operating point C. We shall discuss a problem for this. Okay. Yeah, we can go through this table for understanding. So let us see a problem on this dynamic braking. A 440 volts DC separately excited motor has a rated armature current of 76 amperes at a speed of 1000 revolutions per minute. The armature resistance of the motor is 0.377 ohms. Assume that the load torque is gravitational. So what does it mean? Load torque is gravitational means load torque is unidirectional. Current is not changing. A dynamic braking technique employing a braking resistance of 2 ohms is used. So braking resistance value is also given. Calculate the new steady state speed. So if I include the braking resistance 2 ohms, will it go to zero speed or will it attain any steady state speed that you calculate now? Yeah. So this is the one. Initially, the switch is at the point A. Motoring operation was going on. This is applied voltage V or VT, and then you have the current. So during braking operation, the switch is moved to point B, and hence the braking resistance is included. So EB is VT minus IARA. From that, you can find the back EMF, and then calculate K into phi product. This is very much essential. Same steps for different problems. So its value is 3.93. Now, as it is given that the load torque is unidirectional, the point A when external resistance RB is connected will not go to B, but will go to point C. Okay, so what is the current equation? IC is minus KE phi omega C by RA plus RB. So substitute the values, then you will get the omega C and then the speed in RPM. It is minus 439 RPM. So here it comes. It does not go to zero speed. Okay, just go to that problem. Yeah, before it was operating at 1000 RPM. Now it has come to 436 R 439 RPM. Now let us concentrate on dynamic braking with series motors. See, during motoring operation, the external voltage V is connected to series connection of field winding and armature, and current IA is flowing like this. Current IA is flowing in the series field winding from S1 to S2. So this is also the field current and IA, that is armature current. Now, when you are going for braking, that is dynamic braking for series motor, then you are removing the supply and connecting the external resistance RB. So if I directly connect here, what happens? The back EMF will supply the current and current will reverse, field current will change. That is dangerous. And hence you have to maintain same field current direction, but the armature current should reverse. So what we have to do is we have to have an arrangement where RB is connected in the circuit, but IA flows from S1 to S2 only. IF remains same, but IA flows from motor to RB. That is what. So during this case, your series characteristics will be like this. For motoring operations, we had characteristics like this. Okay, so now during braking operation, this curve is shifted to second quadrant for RB1, RB2. When RB1 is greater, it is upwards like this. So you can have different characteristics and hence different speed attainment. Then the third method is the plugging. In case of plugging, what we do for plugging, the supply voltage is reversed. The supply voltage is reversed. So for motoring operation, we are having voltage like this. Now, how you see here we have reversed the supply voltage. Now this V plus terminal is connected to A2 and V minus terminal is connected to A1. So supply voltage is reversed and field current is maintained the same. This is for series motor, okay, where V plus minus is connected to A2 and A1. So for plugging, the supply voltage is reversed. This makes armature current to be reversed and hence negative torque is produced. So for motoring operation, it was like this. If I reverse the voltage, it will not become like this or like this. Now the characteristics is like this. Okay, separately excited series motors. In case of series motor, for plugging, only armature is reversed, not the field current. That you have to be careful there. S1, S2 is there, only the armature winding is reversed. Braking resistance is included in the circuit to limit the current, otherwise a large current will flow. So you can see here the motoring operation characteristics are like this, and the uh, braking operations will be like this. Okay? This is reverse motoring. So advantages of electrical braking is what? It is fast and effective. It does not involve high maintenance cost, and there is no need of replacement of any brake shoes or mechanical parts. Heat generated is very less, and hence the losses are less. So it is having high efficiency. And in electrical braking, a part of electrical energy can be returned back to the supply in case of regenerative braking. That is one much advantageous. Then using electrical braking, the capacity of the system like higher speeds, heavy loads can be increased. That is another advantage. Okay. So please go through this problem and try to understand the exercise problem. So dear students, by this you should be able to determine the motor speed and braking resistance in the motor circuit for any type of braking operation given. So these are the LLPs. Please try to answer this. We'll discuss in class. These are the exercise problems that you can try it out in the textbook of GK Dubai. Okay, students, let us stop here.